Welcome back to the course on architectural design of ICs. So, in the last class we have seen that how this conditional sum adder has been that means what is the architecture for that, how we can that means develop the architecture of conditional sum adder, and the basic starting that means the idea has started from the this carry select adder operation. Okay. So, we are doing what? We are putting a redundant computation, okay, to reduce the number of delay by putting extra hardware to the corresponding circuit. Okay. So, that we have already seen in the last class, and we have seen that why we say that okay, this is the most possible, the fastest adder among all the adders what we have seen till now. Okay, because that the delay level is only one full adder cell plus the multiplexer, the number of multiplexer delay is that is log 2 base n. Okay. So, where n is, if I consider 16 at that time 4 multiplexer delay, if I consider that means consider 8, so at that time 3 multiplexer delay. So, within 8 to 16, so any of this value for n value it will be 4. So, from that means 4 to 8, okay. So, 4 to 8 any value for that, or 4 to 7 if I consider. So, for 4 to 7 any value if I consider. So, at that time this corresponding multiplexer number of multiplexer will be this 3 number of multiplexer. For within 4 bit I need 2 multiplexers, something like this I need to. So, this is but the thing is that whenever we have to design for the disadvantage of conditional sum adder is that as we are increasing the number of this multiplexer, and the circuit becomes much more complex whenever we consider more number of bits. Okay. So, these as though it follows one regular structure, but if we consider that means more number of bits. So, at that time the connection becomes very much that means complicated, as there are so many that means components which you need to wear. So, that becomes very much complex whenever we consider more number of conditional sum adder bit. Okay. So, for that reason there is another adder actually not for that reason, there is to reduce, actually we know that carry lookup adder we generate and then propagate the carry, okay, and based on that we calculate the sum and carry for each of the stage. Okay. So, to reduce the that means, and in the expression what we have seen that this C I plus 1 that is equals to G I plus P I into C I. Okay. So, actually C I plus 1 that is equals to G I plus P I into C I. So, if I consider that I equals to 7, so that means C 8 that has to consider, that has to, for the last term it has to consider this P 7, P 6, P 5, P 4, P 3, P 2, P 1, P 0, and then the input carry which is C 0. So, that means the levels that will increase if I restrict the fan in. So, at the time the levels is increased because of this particular ANDing operation which I required for this G and multiplication of G and P, that means the generation of the this propagation of the carry. Okay. So, to reduce that there is one that means that adder has evolved which is known as Ling adders. Okay. So, then how it reduce this number of that means terms in carry lookup adder, that we will see. So, this is the CLA that means basic CLA operation. So, the PI signal that is AI XOR BI and GI is AI dot BI, whereas CI plus 1 that has been generated based on this GI plus PI into CI, and SI is generated from PI XOR with CI. But according to Ling's equation, they have modified the equation in such a way so that it can reduce the number of terms which are related, which are coming for this particular things. So, it says that this Ti equals to Ai plus Bi and Gi equals to Ai dot Bi, and this Hi plus 1 equals to Gi plus Ti minus 1 dot Hi. Okay. So, initially what was there, that means that was Pi was Ai XOR Bi, but here this is OR, okay, and that is this Ti minus 1, and this S has been calculated based on this Ti XOR with Hi plus 1 plus Gi into Ti minus 1 into Hi. So, this is the modified equation. If you see, if you just, that means compare these two equation, it is same like the generation or the, that means propagation of this generation and propagation of the carry, where this is basically modified with H, this C is modified, that means changed with or renamed as H here, and S has been, this is not XOR operation, this is with Ci only, this is XOR with this Hi plus 1 along with or with this Gi Ti minus 1 in and Hi. Okay. Then what is that? That means the function of this. So, variation of CLA is, okay, is that Ci plus in Ci plus 1 equals to Gi plus Gi Ci plus Pi in dot Ci. Okay. So, if I just write it in this terms, so at the time Gi will be Gi plus Pi dot Ci. So, this Gi plus Pi, that is as this Ti. Okay. So, and this according to this Ling equation, so this Hi can be written as this Gi plus Ti minus 1 dot Hi minus 1. So, here you see Ling uses different transfer function, 4 of this function have desired properties, Ling is one of them. So, in the conventional method, if I just for C4, if I consider 4 bit, so at that time if you see at the last term, what I said, that at the last term what I need this here, if I instead of that P, if I just replace that with T, so that means I need T3, T2, T1, T0 along with this C in, which is the first carry input bit. But according to the Ling equation, if I just write this, so at that time H4 will be written as T2, T1, T0 in C in. So, that means these 5 requirement in conventional carry loop adder, that has been reduced in Ling equation, where this is basically, that means here if the fan in is 5, here the fan in is 4. So, if the fan in is 4 here and the fan in is of 5 here, that means we can reduce the delay. Okay. So, that means then what is the advantage of Ling adder? Uniform loading in fan in and fan out. This H16 contains 8 terms as compared to G16 that contains 15. Okay. So, that means if I consider this this C16, at that time I need, according to the CLA, I need the term as 15, but here in according to this new equation of H, using this 8 number of terms, I can compute this H16. Then H16 can be implemented with one level of logic, while G16 cannot. Okay. So, that means then obviously, as I can increase or I can decrease that number of logic level, that means I can improve the corresponding speed or the operating frequency of the adder design using this Ling's equation. Okay. And this is basically this 32 bit adder, this Ling's adder, that has been used in IBM 3033 model. Okay. And then that means 3 bit addition in 3 levels of logic, and then 5 level of logic for 64 bit adder used in HP processor. So, that means Ling Adder is very much useful in the earlier days. So, earlier days that processor computer microprocessor. Okay. So, then this is this one work which is basically if you just want to that means know more on this Ling Adder architecture. So, you follow the work on this that means which is that means published in International Solid State Conference in 1996. Okay. So, there you will get how that means the equation has been developed and how the that means from this particular equation how the corresponding architecture has been developed, that you will find that means in details in this particular paper. Okay. So, this is the transistor level implementation of Ling's equation, okay, and all this you will get from this particular paper. So, I am not going into the details of that. Then, so that is the advantage of that means Ling Adder, and what is that? That starting point of that is the Carry-Lucas adder. Okay. Then the present days basically we use this prefix adders or the parallel prefix adders. That means here what we do, that means suppose I need to add two numbers A and B. So, at the time in the that means conditional sum also what we do, we pre-compute those values and then we add, okay, or actually in conditional sum what we do, we pre-compute those values considering 0 and 1 and then based on the multiplexer we basically select which signal I have to pass at the output level. And in Carry-Lucas adder what we do, we basically that means initially from the bit that means input bit we basically generate and then propagate the carry. We have two logic, one for generation of the carry, one for propagation of the carry. Then based on the equation now we are trying to calculate the sum and carry output. So, here also the same thing. Okay. So, it has that means this parallel prefix adder, okay, it has that means this pre-processing and then post-processing that means scheme. So, it has follows two method. Okay. So, in one method there are it follows three step. Step 1 is pre-processing. So, in pre-processing generate the carry using this particular equation and propagate the carry using this particular equation, and then you compute the prefix. So, how you can compute the prefix? The prefix can be computed using GIK. So, that means this is nothing but a actually we will see this the corresponding graph of this different adder architecture, parallel prefix architecture. So, here actually we will get one node, okay, or this will follow one regular structure. Okay. So, considering we have to generate this GIK based on this particular equation. If I and k both the values are same, so at that time GI will be the GIK value, and if it is not, if I and k they are not same, so at that time I have to do Gij plus Pij in dot Gj minus 1 k. Okay. So, that means this is the coordinate of G and P which are basically presented within this parenthesis. So, then again for P this is for G and this is for P, again we have to follow another equation. So, for I equals to k that will be Pi, or otherwise it will be Pij dot Pj minus 1 k. So, then again I need, so once this prefix computation is done based on this post processing of Gi and Pi, then we can go for this post processing for calculating the corresponding final carry in and sum bit. So, the Ci value is Gi 0 and the sum is Pi XOR with Ci minus 1. Okay. So, this finally will generate So, that means this is a simple logic which will generate the corresponding sum and carry for each of this stage. So, that means now if I consider 7 bit, so at that time this will varies from 0 to 7. Then again there is another method where in this method 1 we are taking Gi and Pi. So, in another method we have to that means take, or we can take three variables, that is Gi, Pi and Ki, where Ki is nothing but this NOR operation of Ai and Bi. And then for prefix computation we will use this Ki instead of Pi. In this case we will use this Ki as by following this particular equation, that is Gik, that is Gi and Gij plus K bar Ij dot G into J minus 1 to K. If for I equals to K, that is Gi, for I not equals to K, then this equation, and for Kik, that is for I equals to K, Ki, that means the bar of or the complement of Ki, otherwise Kij dot Kij minus 1 to K otherwise, and then again finally follow the same post processing for final computation of the for each of this position or the each of the stage. That means again same, if the carry, that means I is varying from 0 to 7. So, that means then for 7 this will be this sum and carry that will be computed. Okay. So, then whenever we are computing these parallel prefix arrays, so at that time it has to follow two that means property it has to follow. So, one for that means there are basically two properties which are related to this parallel prefix arrays. So, one of the property is associativity and another that means of the property is idempotent property. Okay. So, the associativity allows pre-computation of subterms of the prefix equation, whereas this idempotency allows these subterms to overlap, which provides some useful flexibility in the parallelization of the corresponding circuit. Okay. So, that means how we can that means define this associativity property. So, if I am having this Gp, this is the dot operation with this Gp of Jk. So, here you see that this is the within this parenthesis that means corresponding term, this is H to J and this is J to K, then I can write H to I to I to K, that means this J can be replaced as with I, and for this K dash, that means this is for method 1 and this is for method 2, where this I am for method 1 I am using P, for method 2 I am using K. So, for method 2 this is G K bar H J, so J to K, so again it can be written as H to I then I to K. Okay. Then for idempotent that means idempotent this property, I can write this as the same, that means where this here for this method 1 it will consider P, for method 2 it will consider K, but the equation is only different. Okay. So, this two property is related to parallel prefix adder computation. So, whenever we are that means telling this dot operation, so what does it means? This simplifies the representation of G along with K or P, P for method 1, K for method 2. An operator called as dot operator represented by star is introduced to create group generate or group kill bar. So, how we can, that means in method 1 this is the dot operation, in method 2 this is the dot operation. Okay. Here you see this is the that means in method 2 this is the dot operation, in method 1 this is the dot operation. Okay. So, what I need is basically, so based on this we have to, that means what we are doing, this prefix we are basically pre-computing, and that is basically work, or that is represented one node. Now, we will follow the, that means one regular structure to compute the corresponding that means the bit or the corresponding, that means the sum and carry value for each of this bit position. Okay. So, how we can do that? Suppose I am having this 16 bit inputs or 16 bit that means addition I require. So, this blank box, this white color box, they represent, or this is nothing but this is the DFG of this this parallel prefix adder, which is known as Sklansky adder. Okay. So, here this basically represent these input nodes, these black boxes, they are represented basically the dot operator. So, dot operator we have already seen that G and K, P for method 1 and G and K for method 2. Okay. So, these are the dot operators and these are the semi dot operators. Okay. And based on that we can get the final output. Okay. So, I need this 4 stage if I am considering this kind of this, that means whenever this will that means the carry from here, that will affect this, then carry from there, that will affect this. So, then again this carry can come to here. So, this is one of the architecture if you follow. So, what we have to do here, we have to compute the prefix based on method 1 or method 2. So, that means this dot operators or this particular semi dot operators based on the equation what we have seen in the earlier section. So, that means now what does it means? This basically needs two that means the coordinates of 2, as if I represent this as a 2D graph. So, at that time, so in this direction and in this direction I need to, that means represent this particular point or this particular node. Okay. So, that is why based on this from which node to which node will be connected. So, that we will get from the corresponding information which we have already mentioned earlier. Okay. So, here in this case if we consider this particular Sklansky adder method or this Sklansky, this is the DFG of this Sklansky adder, if we follow there. So, the number of computational node that will be n by 2 log 2 base n. If n is 16, so then here 8, and for this is 4. So, that means total number of computational node will be 32 and the optimal depth will be log 2 base n, that means that is 16 means 4. Then there is another method which has been proposed by these two particular scientists, this that means Mr. Cog and Mr. Stone. So, they have named this that means adder architecture as Cog-Stone adder. So, there are, that means you see more of the, that means this corresponding, that means operators are overlapped to each other. Okay. So, whenever we are, that means overlap to each other means we are increasing the corresponding number of this computational node. Though that means optimal depth, if I consider the previous case, the optimal depth remains same. Okay. So, the number of these black dots and these gray dots that increases along that means in this particular Coxstone adder. So, here the number of computational node is n log 2 base n minus n plus 1. Then again, to improve the corresponding performance of this Coxstone adder, we have another architecture which is this Brent-Kung adder. So, here what is that means how it has been generated? By setting the fan out to 1, and another that means problem with this is that here more wearings are there. So, to reduce the number of wear, we have that means come to this adder architecture which is Brent-Kung adder. Okay. So, this basically avoids the explosion of wears, which basically happens in that means Coxstone adder, and it is more efficient to inside buffers in that means in compared to this Brent, that means according to this Brent-Kung adder scheme, we can insert the buffer more efficiently. Okay. So, then again if we just follow the circuit, that means the architecture for this Brent-Kung adder. So, here you see this is the architecture for this Brent-Kung adder. Here the number of that means the these nodes that are decreasing, but here you see at the that means with this that means as the number of nodes are increasing, that means decreasing, the number of stage that are basically increasing, sorry, this as the number of nodes are decreasing, but the number of stages are increasing for this Brent-Kung adder. Okay. So, this is the that means the computational node is required this number, and the optimal depth which is can be derived from this particular equation, and n is the that means the bit considered for the adder or the addition operation. Then again whether actually we have this Hankelchen that means this algorithm. Okay. So, this basically is one this is one like hybrid architecture. Okay. And here what we do, we basically do to reduce the number of stages, we use at the very beginning, we use at the very that means in the first we use one different that means this Coxstone architecture, and then in the that means lower portion we use different method to reduce the number of stage, which are the that means this disadvantage of Brent-Kung adder. And here you see by this particular Hankelchen adder, so we can reduce the number of computational node by this and the optimal depth by this. Okay. So, then we will actually this Lander, that means Ladner and Fisher adder, this basically L and F is Ladner and Fisher adder, that means that is the hybrid of this Hankelchen that means adder is the hybrid of this LF and KS, these two. Okay. So, what is there in this Ladner Fisher adder? So, in Ladner Fisher adder it has follows one different topology, where the number of computational node is n by 2 log 2 base n and optimal depth is log 2 n plus 1. So, but that means the number of stage that means remains same, that is 5. So, there are again that means this we have already that means seen this. So, if we just that means see that means what are the that means difference in this particular adder design. If you consider this 8-bit parallel prefix adder, considering different type of adder architecture, the number of dot means that black box or the black circle, and where semi dot means this gray circle, the number of requirement along with this logic depth for 8-bit parallel prefix adder. For Brent-Kung the dot are 4, semi dot are 7 and the logic depth of 4. For Coxstone the dots are more and this semi dot as there are more overlap. Okay. So, that dot are 10, semi dots are 7 and the logic depth that has been reduced, that is 3 by putting, that means parallel computation. Then Hankelsen, that is 574, for Ledner Fischer, that is 573, and this Sklansky, that is 57 with 3, oh sorry 4. So, this is for 8 bit, and then for this is for 16 bit. If you see that which one is the best one from this, if I just, that means try to calculate, this is the minimum number which I am getting for, that means that is the Brent-Kung adder, but the logic depth that has been increased. That means whenever I need area as my major constant, so at that time I will follow Brent-Kung adder, that means I have the liberty, or I can, that means I can, that means leave this speed operation, that means the speed is not that much that means major constant at that time, where area is my major constant. So, at that time I can follow this Brent-Kung adder. Otherwise, if area is my not that major constant, but speed is my major constant. So, at that time we have to follow this Coxstone architecture. So, this is for 16 bit and this is for 32 bit. So, here you see that is 5, for 64 bit that is 16, because that is log 2 base n. So, n 64 means this will be 6, for 128 this will be 7, but the number of dot operation that are on the higher side in compared to this particular 5. So, then if we take this power and delay, if we take this power and delay the consumption of this particular 5 adder architecture, and at that time you see this Sklansky adder, that gives you the lower number of that means power delay product whenever we are that means developing 8 bit parallel prefix adder using 180 nanometer technology. Then this is for 16 bit parallel prefix adder using 180 nanometer technology. Again you just see that the Sklansky, the delay is basically so based on this, this average power consumption is 110, and this corresponding this power delay product, that is 55, which is the minimal one in compared to the other 4 adder architecture. Okay. And then so this is the, that means the structure how we can select. So, this is a pyramid adder and another adder, how we basically do, and we have already seen this. So, the possibilities for further research is that the logic depth is very much important. So, how we can reduce, or whether I can reduce the number of logic depth more, that is one that means is very much, that means important aspect. So, you can, that means further you can just look into that, how we can do that. Then fan out is less important than fan in, because if we restrict the fan in, so at that time the levels will increase. So, it is possible to examine a variety of topologies with restricted and varied fan in. So, that is also another, that means direction of further research. Then driving strength and the logical effort rules were overlooked and at least neglected. It is possible to create number of topologies like this logic element rules into account, and it is further possible to combine the rules with compound domino implementation, taking advantage of 2 different rules governing dynamic and static. It is still possible to produce a better adder. So, that means there is a so considering this particular that means adders things, we can take, that means different combination of this prefix addition. Okay. So, different, what will be the combination, that means what will be the optimized combination of, so that I can get in terms of minimized number of this dot and semi dot operation, along with the logical depth will be on the reduced or on the lower side. Okay. So, both the things if we can optimize, at that time obviously I will get one very good adder architecture. Okay. So, along with this, this is the end of this adder architecture. Okay. In the future, that means we will again start with a new chapter in the next class, which is this different. We will see now this multiplier architecture, different multiplier architecture that we will see. Okay. So, thank you for today.